In this unit of AP Biology, we're going to begin discussing photosynthesis. In this unit, we'll cover the following topics: light and energy, the origin of photosynthesis and ATP, prokaryotic photosynthesis, the evolution of photosynthesis, photosynthesis chemical reaction, and eukaryotic photosynthesis. Before we begin a detailed discussion of photosynthesis and the reactions that occur, we're going to start with a little bit of an understanding of light and energy. Sunlight provides the energy for life on Earth's surface through photosynthesis. A similar process without the need for light supports life near deep ocean thermal vents. Sunlight makes the life around us and us possible. Photosynthesis is a word made up of photo, that refers to light, and synthesis, which refers to making something. Light is used to make glucose from water and carbon dioxide. The energy of life supplied by the sun begins as photons. Photons are little packets of electromagnetic radiation or light. These photons are created by nuclear fusion traveling out of the sun at the speed of light. In order to understand photosynthesis, we need to first understand how photons are able to transport energy from the sun all the way to plants on Earth. And then, how do plants absorb this light energy using pigments? On the previous slide, we had said that photons are tiny packets of electromagnetic radiation. Well, what is electromagnetic radiation? It is oscillating waves of magnetic and electric fields. So you can see one of the waves in red oscillating up and down, and the other in blue oscillating in and out of the page. This radiation travels through space at the speed of light, which is given by the symbol c. The distance between the crests, which you can see labeled here from the red peak to the next red peak, is the wavelength given by the Greek symbol lambda, and the number of crests per unit time, or how close the crests are together or how often the crests repeat themselves, determines the frequency, or F. The wavelength, frequency, and speed of light are related by this equation, where the wavelength, lambda, is equal to the speed of light, c, divided by the frequency, f. The energy of the radiation, or how much energy the photon has, or how much energy the electromagnetic radiation has, depends on the frequency of the photon. So the energy, E, is equal to H times F, where F is the frequency, the same frequency as above, and H is a constant. It's known as Planck's constant or Planck's constant, and it equals 6.626 times 10 to the minus 34 joule seconds. Here are some relationships that are worth knowing. If the wavelength is short, then the frequency is high and the energy is high. And remember that wavelength is measured from peak to peak, okay? If the wavelength is long, so let me stretch this wave out a little bit. So this is a much longer wavelength, then the frequency is low and the energy is low. So the wave that I drew on the left would have a higher energy than the wavelength on the right, which would have a lower energy. Electromagnetic, or EM, radiation covers a wide spectrum of wavelengths and frequencies. Visible light occupies a small sliver of that spectrum. You can see that small sliver right here between UV and infrared. And it has wavelengths starting at 400 nanometers and going to 700 nanometers. So blue-purple light has the shortest wavelength. And remember from the previous slide, the shortest wavelength is the higher energy. And red light with a longer wavelength at 700 nanometers has lower energy. This chart shows the relationship between wavelength, color, and the energy of the visible light. Light with shorter wavelengths have higher frequency and greater energy. So I talked about this a little bit on the previous slide. These shorter wavelength light, the purple light on the far left at 400 nanometers, has an energy of 3.1 electron volts. An electron volt is 1.6 times 10 to the minus 19 joules. Okay, so this is just a unit of energy. What happens to that energy as the wavelength lengthens? We can see that at these much higher wavelengths or longer wavelengths, the energy is much lower. So at 780 nanometers, the energy is 1.6 electron volts. When people see a color, green for example, like you see in this image, from an object, it's because the object is absorbing some light waves while reflecting others. White light contains all color wavelengths. In this example, all colors except green are being absorbed, and the green is reflected back to the eye, and your brain sees it as green. Pigments. Pigments are substances that have the ability to absorb light. Humans perceive their color as the wavelengths that are not absorbed. So if light is shined here, everything except for the blue is absorbed, and the blue is what is reflected back, and we perceive this pigment or this color as the wavelength that is not absorbed. When electromagnetic radiation is absorbed, the energy contained in the photon is transferred to an electron. The electron is excited, moving it from a lower energy level to a higher energy level. So look what happens here. This photon of light, this electromagnetic radiation, is being absorbed. In doing so, this proton right here is moving from n equals 1, the ground state, to n equals 3, an excited state. An excited electron is unstable in that higher energy level and must release the energy it gained from the photon. In a pigment molecule, the energy can be released in several ways: fluorescence, reaction initiation, and resonance transfer. Fluorescence. In fluorescence, the electron releases its energy, emitting a photon as it drops back down to its ground state. So remember a previous slide, a photon was absorbed to move this electron to n equals 3. When the electron falls back down to its ground state, n equals 1, a photon is emitted. For fluorescence, the energy and the frequency of the photon released is slightly less than the energy and frequency of the initial photon. Reaction initiation. The excited electron could also provide the activation energy necessary to initiate a chemical reaction. For example, iodine is kept in dark-colored bottles because exposure to light, absorbing those photons, initiates a reaction that degrades the iodine. Resonance transfer. If the excited electron is near another pigment molecule, it can transfer its energy to an electron in the neighboring pigment molecule through a process called resonance transfer. The energy will continue to move between donor and acceptor pigment molecules without releasing a photon. So look what happens here. The light is absorbed on this pigment molecule here, and then we have this resonance transfer throughout all these neighboring pigment molecules. And so at this point in time, this is my reaction center, and here's my pigment molecule with the excited electron.